Welcome. In this video, we will be discussing about the relationship between DFT and DTFT. So let's see, how do we obtain DFT from DTFT? So we do it by sampling. You remember, DTFT is a continuous in frequency, but DFT is discrete in frequency. The relationship is that DFT is simply samples from DTFT. How? Okay, just remember this mnemonic which we had seen in the previous videos: continuous, discrete, periodic, aperiodic. If signal is continuous, the transform is aperiodic. If signal is discrete, the transform is periodic, and vice versa. Which means if the signal is periodic, transform is discrete, signal is aperiodic, transform is continuous. Given, now let's come back to our problem. Given the DTFT x e to the power j omega, we want to find the DFT xk. So DTFT, you remember, it's given by xn e to the power minus j omega n. And the thing is that here my xn is a discrete time signal, a discrete sequence, and it can be of any length. It's aperiodic, any length. Since this is aperiodic, the corresponding Fourier transform will be continuous. That's why we get x e to the power j omega. But you also know xn is discrete, so my capital X will be periodic, right? Now let's look at DFT. What is DFT? X of k is xn e to the power minus j 2 pi k upon capital N times small n summed over all n. In this case, what we see, the relationship is this xk is simply x e to the power j omega, where omega is replaced by 2 pi k upon n, right? From this simple comparison, we can see that this omega is replaced by 2 pi k upon capital N. Now let's look at the nature of this DFT transform. Here we see my xn is finite. What does that mean? See the limits. N goes only from 0 to n minus 1. And it is assumed that at other values of n, xn is periodically repeating. Since it is a periodic signal, we need not worry about that part. We only need to worry about the single cell which is repeating, and that cell is n equal to 0 to capital N minus 1. So since we have a finite xn or a periodic xn and single cell is finite, so that therefore from periodic we go to discrete. That is why my capital X is discrete in nature. So periodic xn leads to discrete capital X. This is the simple visualization of DFT versus DTFT. To be more graphic, you can see x e to the power j omega was a continuous representation, continuous in omega, and my xk is discrete in omega. Right, so my omega is 0 to 2 pi, k is 0 to capital N. And when k is capital N, the value is same as k equal to 0 because of periodicity of xk. So my xn is periodic as well as xk is periodic. You know that x e to the power j omega is also periodic. Now let's look at the other side. The other way around, how do we obtain DTFT from DFT? So given DFT, the discrete samples, how do we find the continuous signal, the continuous x e to the power j omega, continuous spectrum? So the simple answer is by interpolation. You interpolate and then you find the values. So these are the values at 2 pi k upon capital N. And these are the values for any omega between 0 to 2 pi. and you can obtain it by interpolation. Let's see how can we derive this from our standard formulas, and what kind of interpolation is suggested by those standard formulas. So let's look at capital X e to the power j omega, the continuous thing. So you know it is this. Now I do not know xn. So I obtain my xn from xk, which I know, right? I know xk. So I obtain xn from xk and use it to find x e to the power j omega. So therefore I replace my xn with the inverse DFT of xk, right? And now if I substitute this value in this form and I just do a little bit rearrangement, I take this k summation outside and n summation inside, basically xk is thrown out, and what I am now concerned with is this exponential minus j omega n plus j 2 pi k upon n. Now let's look at the nature of this term, this summation. So this summation is, you can take the j out and n out, and this is the thing. Let's do the summation now. Okay, just a little bit simplification. We replace this term with theta, where theta is omega minus 2 pi k upon capital N. Just a substitution so that our thing becomes easier to compute. Now we have to find the summation over this term. Okay, let's write it down again. Now this is the thing which we want to find. You know this is a geometric progression, sum of terms in a geometric progression, and you can recall the sum of GP is given by 1 minus e to the power minus j theta, means the common ratio r power capital N, which is total number of terms, divided by 1 minus r. The common ratio r is e to the power minus j theta, right? Now let's put it back in our original formula. Okay, so some simplification can be done, that this thing can be written in terms of sinusoids and cosinusoids. Basically, why I am doing it, I want to find out the magnitude of this term and the phase of this term. I want to separate the magnitude with the phase so that I can probe more into the nature of this term. So okay, to find the magnitude, a simple trick is I can represent it in terms of sine and cosine, and I know e to the power something or j theta minus e to the power minus j theta is the sine of theta into j. So if I substitute that, what I get is sine of this theta n upon 2 divided by sine of theta upon 2, right? And the phase terms are all outside. So, and this phase term I know it's a single phase term. Now put back the value of theta, and what do I get? I get this full expression. You remember the value of theta which we had substituted, omega minus 2 pi k upon n. This is what I have put back now. So this is the phase term and this is the magnitude term. Now we can probe more into the nature of this whole formula. So let's write it down again. My x e to the power j omega is simply xk times this term, and where this term is given by sine upon n times sine e to the power this thing, right? This is the overall formula which we have obtained. Now I want to know the nature of this term, because you remember this is the term which is doing interpolation over these values. Okay, let's look at the nature of this term. Sine of omega n upon 2 is given by this, right? What is the periodicity? So basically, my omega, I know it goes from 0 to 2 pi. So the time period, the frequency okay, let's say in 0 to 2 pi, how many cycles will I have? If there were no n upon 2, I would have had single cycle or 2 half cycles. But now in this case, I will have, when omega is 2 pi, I get pi n, means n half cycles. So I'll just write it down again. Uh, when omega, okay, so omega dash goes from 0 to 2 pi, right? And at omega dash equal to 2 pi, uh, uh, this term omega dash n by 2 is equal to pi n. So this implies n half cycles of sine. So my sine of this term will take capital N half cycles. What does that mean? So 1, 2, 3, 4. So 4 half cycles. Similarly here, n will have just 1 half cycle, because when omega is 2 pi, I get sine of pi, which means just a half cycle. Let's draw that again. So when sine omega dash, the denominator term, sine omega dash upon 2, it looks just 1 half cycle. Right? Now let's plot this whole overall term. Okay, this overall term looks very simple at other places, only at this place it is problematic, because both numerator as well as denominator go to 0. Now how do we deal with that situation? You know, we use L'Hopital's rule. It says you differentiate this term and differentiate this term, and so what you get basically is omega dash n upon 2 divided by omega dash n upon 2. So both terms cancel out, it becomes 1. The magnitude term becomes 1 at omega dash tending to 0, as well as omega dash tending to 2 pi, because it's a periodic thing. Right? Okay, so let's plot the magnitude of this beast. It looks like this. So you know, here your numerator is 0, here it is 0, here it is 0. So you get zeros here. Because it is just magnitude, so these negative terms also become positive. And you know, at 0, the magnitude is right 1. And about here in the middle, let's say here in the middle, it will be this much, means 1 upon this, whatever is close to 1, into capital N also is there. So it will be a very small value. Right? So larger the value of capital N, the smaller will be the value of these side lobes. Okay, now let's look at the entire formula. How does this look like? Okay. Yes. So my orange thing is the overall x e to the power j omega. And how did we obtain it? Let's start from the green signal. The green signal is at k equal to 0. So when xk, x0, and phi of, when this part is 0, it's just phi of omega, which means just this thing comes. That's what I have done. The green part is just this phi of omega. Now when k is 1, this is 2 pi upon n. So this whole thing is shifted by 2 pi by n. So that's why we shift it, and here the magnitude would have been 1 for phi multiplied by xk, so x of 1. So this part is exactly equal to x of 1, right? And subsequently it is just this thing repeated. So that's what, since this is periodic, so on the left hand side also you will get the same thing. And then at k equal to 2, this is omega minus 4 pi upon capital N. So this is again shifted version of, so basically it will be the same shifted version of this, right? So phi is shifted by that much amount. Okay. So in this way we see the interpolation is done by this capital phi. Okay. Now let's look at sampling the DTFT. What does this mean? Uh, um, Here we show that how sampling in the Fourier domain leads to periodicity in the time domain. Let us say my xn, where n belongs to integers, has a DTFT x e to the power j omega. We sample yk. So yk are the samples of x e to the power j omega, sampled at omega at 2 pi k upon capital N, where k goes from 0 to n minus 1. So basically, I have taken capital N samples. So my x e to the power j omega, which lies from 0 to 2 pi, I take 1, 2, 3, 4, like that, capital N samples. So for some value of capital N, which is a positive integer. Now, what will be yn, the inverse DFT of yk? So remember, we start from some xn, which was very long, potentially infinite, and I take the DTFT, I get the x e to the power j omega, which contains all the information of this infinitely long sequence, x of n. Now I sample x e to the power j omega. By sampling x e to the power j omega, I am giving away so much of information, right? So I obtain yk. Now if I take the inverse DFT of yk, how will my inverse DFT or the yn look like? Remember, my xn was potentially infinite, but my yn will have only capital N samples because it is inverse DFT of yk, which only has capital N samples. And this will be only capital N samples in y of n. And I want to know what is the nature of these capital N samples. So what you will ultimately find is that these samples are repeating. This is one cell, and this thing repeats another cell. So this is periodic. So although my xn was aperiodic, if I go to the Fourier domain and sample in the Fourier domain and again come back to my time domain, I see that sampling in the Fourier domain has induced periodicity in the time domain. But we will prove this now, how that actually happens. Let's see. So let's start from x e to the power j omega, which is a periodic thing which I want to sample. So the relation, all of you know, it's given by xn into e to the power minus j omega n summed over all n, and omega lies between 0 to 2 pi because it's a periodic transform. Now, if I sample x e to the power j omega at omega equal to 2 pi k upon capital M, right? So I obtain yk. Yes, this is also very clear. Now I have to take the inverse DTFT. Okay, so this is just substitution of this omega into this formula. Now I have to take the inverse DFT of yk. If I take the inverse DFT of yk, what do I obtain? My small y of n is equal to this thing. This is standard formula for inverse DFT, right? Let us substitute the value of yk which we have obtained from here. So value of yk is this thing, this whole thing comes here. Now what I see is this is the form, and I know what I am going to do next. The L thing will go out, K thing will come in, so that I can simplify this product of two exponentials. That's what I do here now. And the product of these two exponentials, they take a very nice form. Let us look at the nature of this summation now. So I'll write it down again. So this was the form of yn which I had obtained in the previous slide. I'm repeating it now here. Okay, let's look at the form of this. So this is simply, GP and sum of terms of a geometric progression. The sum is given by this thing, and if n is not equal to L, then e to the power j 2 pi times some integer which is equal to e to the power j 0, so it is 1 again, so this is 0. So if n is not equal to L, this whole sum is given by 0. But if n is equal to small l, then I find this term becomes 0, so e to the power 0 is 1, summed over k going from 0 to capital N minus 1. So sum of n times 1, so just capital N, right? So in other words, I can say this whole thing is given by delta of n minus L times capital N, right? And you know that this thing is repeating because this whole thing is defined only for the values of small n which are between 0 to capital N minus 1. But if I have to repeat it over other values of small n, then I get n minus L plus mn. So it is repeating at an interval of capital N, right? So this point is little subtle. You might be able to appreciate it. So it comes from this formula basically. If you don't constrain n to take values only between 0 to capital N minus 1, you will see at values of small n, let us say after capital N minus 1, which means capital N, n plus 1, n plus 2. There you will see, if you compute this formula, it will be repeating and you will get this kind of a sum. Okay, so ultimately what do we obtain? We obtain y of n is simply, so here because it's a summation over L, so the L thing will go away because basically delta of L will be equal to, delta of this whole thing will be equal to 1 only when this whole thing is equal to 0, which means L is equal to n plus mn. That's what I have done here. So I have replaced L with n plus mn. So this is a formula which we have derived. So what does this look like? This means my xn is periodic now with a period of capital N. We will look at this in more detail. Let us consider this form and see it in little more detail. Okay, I will be considering one example to illustrate how this looks like. Let us say xn is 5, 4, 3, 2, 1, 1, 1. This is a sequence of length 7. Now we compute x e to the power j omega, no problem. This is very simple. Now we get yk by sampling x e to the power j omega at omega k at these intervals, which means basically my capital N is how much? 4. I think it should be 3. I take my capital N to be 4 and this is what I obtain. Now, if we take inverse DFT of yk to get yn, then what do we obtain? We have just derived that it will look something like this, x of n plus m capital N, right? So let's draw it. So my xn was something like this, right? 5, 4, 3, 2, 1 and 1, 1, 1. And when I take the x e to the power j omega, it will look something like this. I have used Python programming to plot it and to compute it, but it will look something like this. From 0 to 2 pi, this is 2 pi, 0 to 2 into 3.14, so approximately 6.28 here. Now I sample it. So by sampling, I obtain this value and then this value somewhere around before 2 and then somewhere in the middle at omega equal to pi, and then out here you see there is a periodicity here, like it goes like this, okay. And then if I take the inverse DFT of yk, I obtain my yn, which is something like this. So remember my capital N was equal to 4, right? This is all done by program, but what I want to show is this. How do we obtain yn from xn? So what has happened is basically you have your xn and you get your xn folded over. Basically, the values were allowed only from 0 to 3 because these things were repeating. And what I see is if I repeat xn, these values, they are falling in the same window, so they get added up, and subsequently these values are repeating. So what I obtained finally is this. So, and you see this was 5 4 3 2 1 1 1. So 5 4 3 2 and 1 1 1 get folded over it because you remember the form, my y of n is equal to x of n plus m times capital N summation over all m, basically from minus infinity to plus infinity. What you see here is, so this was my x of n, this was my x of m plus capital N, x of m, n minus capital N minus 2 capital N. In this way, I have written down all xn. So basically, this is x of n, this is x of n plus capital N, this is x of n minus capital N, because my m can take values from minus infinity to plus infinity, xn minus 2, and that is why it is shifted. So this was my thing, and this is shifted. Right? Now, what I have obtained is this thing. So a more pictorial representation of this is something like this. So originally you have a linear scale small n which goes from minus infinity to plus infinity, no problem. But since my capital N is equal to 4, I get these markers 0, 4, and what I get is this line gets broken or folded over to get basically this 4 matches 0, 5 matches 1, and 6 matches 3, and their corresponding x of n get added up to form the new y of n. Another way to look at this is this circular representation where it gets folded over, and so the value at 0 adds the value at 1, value at 1 adds the value at 5, value at 2 adds the value of 6, and similarly 3 will add to 7. So this is called folding or periodic boundary. This is an important concept in analyzing DFT, that how your xn gets changed. So this is the Python program which I use to plot these things. It's simply NumPy and matplotlib libraries have been used. I plot the discrete thing, this plotting functions. So let's come back to our question 5 4 3 2 1 1 1, and if I plot it, it will look something like this. See, at 0 it is 5, then 4, then 3 2 1 1 1. Okay, now I take the DFT. How do I compute the DFT? I have my capital X, I took an NFFT, I took a DFT basically at very large capital N, and then I interpolated, and this was all trick done to compute my x e to the power j omega in Python. So don't worry about this part for the time being. And this was my x e to the power j omega, basically the magnitude of it. Now if I sample it, so what I find is this. So how do I sample? I used some approximation and sampled at values of omega k, which are like this. And then I computed the inverse Fourier transform of capital Y. Why have I taken real here? Because what I found is that my Y, ideally it should be a real thing because my capital Y was of that nature. Basically, if you remember, a real signal, the Fourier transform is the magnitude function is an even function. Uh, so if my ym is real, then my yk is yk is equal to I think there's a negative sign here, I'm not sure. Okay. So in this way my y will be a real thing, but what I find is it is a real it is a large real part plus uh, some very small let's say 10 to the power minus 16 imaginary part. Just to ignore it, I've taken a real part here. Okay. And so this is how I obtain the inverse DFT, and you can see it is 5 plus 1, 4 plus 1, 3 plus 1, and this was simply 2. No change in here. Thank you very much.